Hi everyone, my name is Huiyu Gao from Australian National University. In this video, I'm going to introduce our work, SOAF, Scene Occlusion Aware Neuroacoustic Field. This is a joint work with Jiahao Ma, David Amanda Risty-Zabral, Chong Wing, and Miao Liu. In this work, we tackle the problem of novel view acoustic synthesis. Given audiovisual observations captured at multiple known pulses in an environment, where each observation consists of an RGB image and a synchronized binaural audio recorded by a camera-microphone pair. Our goal is to synthesize spatial audio at arbitrary novel receiver viewpoint, conditioned on the audio signal emitted by the sound source. To achieve this, we aim to learn a synthesis function f theta that models the scene's acoustic field and allows us to generate binaural audio that reflects how the source sound would be perceived at the target viewpoint and matches the corresponding visual content at the same view. Importantly, our input audio is not restricted to room impulse responses, but can be general reverberant audio recordings, which are much easier to collect in our real-world scenarios. Existing methods typically use visual features from the target viewpoint to generate spatial audio. Thus, their performance mainly depends on the local perspective cues and positional information. However, local observations are insufficient to capture the global scene context, especially when the sound source is not directly visible or lies outside the receiver's field of view. As shown in the right figure, when the sound source is occluded by walls or located in a separate room, local visual cues cannot provide the critical spatial relationship between the source and receiver. In addition, prior approaches rely on purely data-driven learning for the sound field and struggle to encode the acoustic effects caused by scene geometry, particularly word occlusions in sound propagation. To solve this problem, we propose a new approach called Scene Occlusion-Aware Neuroacoustic Field for accurate audio generation. Specifically, we derive scene occlusion-aware global priors based on the room geometry recovered from visual frames, allowing us to explicitly incorporate global spatial cues and extract effective acoustic features around the receiver to enhance the learning of acoustic field. In order to generate binaural audio, we also introduce a direction-aware attention mechanism to extract different features for the left and right channels, leading to audio synthesis with improved binaural effects. Extensive experiments on the real-world dataset and synthetic dataset demonstrate the effectiveness of our approach. Here is the overall pipeline of our method. Given the input video with synchronized binaural audio, our method first reconstructs the 3D geometry of the scene from visual frames, then build the global and local acoustic field for spatial acoustic feature extraction. Specifically, we derive a global prior for any point in the environment by considering two important factors: distance-aware attenuation and occlusion-aware transmittance. When sound propagates in free space, its intensity decreases as the propagation distance increases. As illustrated in the right figure, the energy emitted by the sound source spreads over an expanding spherical surface. When the travel distance doubles, the energy is distributed over 4 times the area, thus the intensity drops to 1/4. Inspired by this, we quantify the distance-aware prior following the inverse square law, where the value at each point is inversely proportional to the square of the distance from the sound source. After that, we check the existence of word occlusions and incorporate the effect of room geometry on sound propagation. Compared to light, Sound waves have much longer wavelengths, so they can diffract around small obstacles and propagate further. However, they are still strongly influenced by large structures, particularly walls in indoor environments. When the sound wave encounters a wall, only part of the energy can pass through the barrier from one side to another. To model this effect, we introduce a transmission coefficient tau, which is defined as a ratio of the transmitted energy to the incident energy. Finally, we assign each point a global prior value that incorporates both distance and occlusion information. Here, n denotes the number of walls found between the point and the sound source. To extract the local acoustic feature, we uniformly sample multiple points around the receiver using a Fibonacci sphere and collect the prior values of these sampled points in the global acoustic field. Then we refine the local acoustic feature using an acoustic encoder and combine it with the visual features extracted from the novel view images, as well as the receiver's positional encoding, to obtain an aggregated feature at the receiver through MLP layers. Moreover, we propose to apply a direction-aware attention to the local acoustic field, generating different features for the left and right channels. Specifically, we compute channel-specific attention based on the similarity between the directions of the left or right channel and the sampling directions around the receiver. By applying the resulting attention weights to the local acoustic features, we obtain binaural features that distinguish the left and right channels. Finally, given the aggregated feature and the channel features conditioned on the receiver pulse, we predict the mixture and left-right channel acoustic masks, then apply them to the source audio spectrogram to achieve binaural audio synthesis. We optimize our network by minimizing the magnitude distance between the ground truth and synthesized audio after applying the short-time Fourier transform. Here, the first turn of the loss function encourages the network to capture special effects that induced by distance and geometric occlusion, while the second and third turns encourages the network to learn discriminative masks for the left and right channels. To evaluate our method, we conduct experiments on real-world and synthetic datasets and keep the same data split as previous works for fair comparison. On both datasets, our method outperforms existing works in all evaluation metrics. For all of these metrics, lower is better. On the real-world AVS dataset, the MAG metric evaluates the generated audio in the time-frequency domain after applying the short-time Fourier transform, while the ENV metric measures the generated audio in time domain. Compared to previous works, our approach achieved better performance across all environments in spatial audio generation. On sound spaces, we adapt our method to predict room impulse responses without any architectural changes or additional supervision. The consistent improvements further demonstrate the effectiveness of our proposed priors in guiding the learning of acoustic fields. Here is a visual comparison of the novel view audio synthesized by our method and the baseline AV-nerve. When the sound source is occluded by the wall, our method generates audio with more accurate energy attenuation. To validate the contribution of our proposed components, we conduct ablation studies by incrementally incorporating each module and observe consistent performance improvements. Also, in order to evaluate the robustness of our approach to 3D reconstruction quality, we compare audio synthesis results in relation to the reconstruction accuracy. The audio synthesis performance keeps stable when the error remains below 6.5. More results are available in our original paper. Thanks for your watching.